What did they pick as their definition to explain those two reactivities?
Looks like nucleophile.
Okay, they started with nucleophiles. And if we go through and look at nucleophile characteristic, what does the nucleophile need to do? Right, donate electrons or an electron donor. Which one do you think they said was the strongest nucleophile?
One on the right.
Okay, so now the question becomes why? Which atom do you think they were defining as the nucleophile? The oxygen gets a little bit dicey when you're telling me that the strongest one has two oxygens. So which oxygen are they saying is the strongest nucleophile? We're comparing the top one when we're talking about that nucleophilic characteristic, right? Okay. So if we're going through and evaluating that as our nucleophile, why are they saying that one is better at donating electrons than the other one?
That one's better at donating electrons?
Well, they circled this one. Why are they saying that one's the... What about the resonance?
More opportunities for resonance?
If there's more resonance, what does that do typically to the reactivity? Stabilizes it, and yet they're saying that one with more resonance is more active. So I don't know that I like that argument. Admittedly, it's not wrong. What resonance structures did they draw?
Oh, they allowed it to have more electrons on that.
They noticed that the carbonyl does do resonance. Is everybody just being quiet? What's going on? Okay, no, that's fine. I just wanted to make sure. Okay, they went through and looked at the carbonyl, but doesn't the other one have that same resonance with the carbonyl?
It's octet.
They have the same octet issues. What else did they do? They recognized that the other oxygen had another resonance option. Okay. We don't invalidate octets or anything like that, so now the question becomes, why does that matter? Yes, we have more resonance, but what did that do to the nucleophilic oxygen? Okay. So we've got those three resonance structures. Which resonance structure is correct? Which is always a challenging question, particularly in the phrasing. It's resonance. They all are. So if we want to evaluate the charge on that oxygen, because again, we want to recognize what element is doing or what atom is doing our nucleophilic characteristics, we want to evaluate that charge on that atom through all of our resonance structures. And we go through and do that, we start with neutral, negative, and negative. The effective negative charge on that oxygen is now negative 2/3. If we go through and look at the other structure with just that one resonance, what's the effective negative charge? Negative 1/2. Starts neutral and it becomes negative. Which is more negative, a negative 1/2 or a negative 2/3? Negative 2/3, which means that one has more electron density, and since it has more electron density, that fits the nucleophile definition better. Neat. Questions?
Down there's 3 places for the electrons to resonate. But now
There's 3 structures that we could use to represent the
2
resonance
of
structure.
them where it have the negative.
Show the negative charge on it. This is why resonance is so powerful, because it allows us to see where the electron density is now moving. Okay, kind of makes sense? Yeah, that's what I'm trying to find out. They said they answered the next question. The next question that I posed to the next group is, since we defined it as a nucleophile, could we have defined it as something else? Hell yeah, we can always define it as something else. And I told them to define it as an electrophile. What's the definition for your electrophile?
Accepts.
Your electrophile is an electron acceptor. Does that change our answer? The nucleophile is which one was more negative. What's the electrophile? Which one's more positive? So right out of the gate, what do you think you should say?
It's the same one.
The same structure can be both more negative and more positive than something else?
Because it spreads
That's a bit sketchy.
there's more positives in the resonance structure.
Okay. And I'm unfortunately erased all my resonance structures. Yes, it has more positives, but again, where do we start? Once you've defined it as acting as an electrophile, the thing that you need to do is identify the atom that is acting as the electrophile. what is the atom that is acting as the electrophile? The electrophile needs to be an electron acceptor. The oxygen has electrons, therefore it is very likely to not be the acceptor. What's our acceptor? The carbon. Once you've identified that carbon as our electrophile, that's where our focus needs to maintain. So when you're going through and saying, but don't I have a positive oxygen? You do. That's perfectly valid. Do I care about the positive oxygen? My focus needs to be where I said the electrophile characteristic was, which was on that carbon. So when I go through and again evaluate the resonance structures, what I'm going to find is I can put a slightly more positive charge on the other structure than on the one with the oxygen. Why? Because the one with the extra oxygen has a resonance contributor where the oxygen is sharing electrons in. Because that oxygen sharing electrons in, what happens to the positive charge? Goes down. That changes its electrophilic characteristics. Okay? Let's double back to the oxygen. Well, should the oxygen have been the electrophile? I mean, it is positively charged. Define the electrophile. I already defined it. I'm not trying to be tricky. What was the electrophile? An electron acceptor. So we'd have to bring electrons into that oxygen. How many electrons are currently around that oxygen? 2, 4, 6, 8. Can it accept more electrons? Even though it is positive, it is not the electrophile. It can't accept more electrons from outside the molecule. It would accept them from within, from that pi bond, therefore making the carbon our electrophile. So jumping on positive charges to explain positives or negatives, electrophiles or nucleophiles is great, but you do have to realize there's a resonance potential that could mess with your initial interpretation. Kind of, sort of? Okay. You guys can sit or kind of join the other groups as we navigate.
Wait, when's our next exam? The 10th or the 7th?
Yes.
I asked you to... Okay, that's it.
Okay. So, in looking at our middle section now, what's going through and doing our ranking now? So, what do we think they decided to rank based off of? What did they define as? What did they define? They defined them as nucleophiles. Why did they not define them as acids? The bromine doesn't have any hydrogen, so it by definition can't act as what we would define as an acid. How about why not define as electrophiles?
They don't accept electrons.
Electrophiles accept electrons. Can either of those structures accept electrons? No, they're negative, so it doesn't make sense to define it as either an acid or as an electrophile, which then means we're definitely looking at a nucleophile. What did they decide to rank based off of? Size. So they'll go through our charge ranking system. Charge, size. Bromine is larger. What does that mean it does to the electrons? Space them out. And if they're spaced out, what does that do to its reactivity? Decreases it, which means the nitrogen will be the stronger base. Okay? Because I'm seeing everybody shift back to their tables, I'll try and talk through these louder. If you guys want to sit, you can go ahead and sit wherever you want to. So when we're looking at this middle one, okay, our nitrogen, I just talked through it for the sake of the recording, but the nitrogen is going to be our stronger base, nucleophile, because it is smaller than the bromide. Okay? When looking at nucleophile strength, so this particular question was relatively straightforward. It could really only act as a nucleophile. But when going through and looking at nucleophile strength can get tricky. And it gets tricky depending on the solvent that you're in. So for the sake of the activity where we walked around and looked at these boards, we modified this particular question and said, yes, now that you've done a good job identifying it as a nucleophile and the nitrogen because it is smaller, now I want to know what is the solvent effect. So as part of that explanation, what I had the group first do was define each of the solvents. So when we're talking about our solvents, we have protic, we have polar aprotic, and we have our nonpolar. Okay? All of those were defined unit 1. So that theoretically now all you're doing is translating up and saying when I look at this structure that acts as a solvent, can I classify it according to those things without having to also think about that? Why do we want to be able to do that? Because now we have to apply that solvent to how it affects nucleophile strength. Right? So what we need to do is just pick a solvent and just go, what does it do? Right? The example shown up on the boards was a pretty dang good job, so toast to that. If we go through and evaluate what's happening with our protic solvent, pick an example. Okay? Water is a good protic solvent. And when we look at the protic solvent, we're generating a large partial positive on our hydrogen and a large partial negative on our oxygen. Why? Difference in electronegativity between the oxygen and the hydrogen. We could also push and call that a polar covalent bond. All of that content is unit 1 content so that you can manipulate and control that here. Why does that become important to us? What we're concerned about is how that protic solvent interacts with our nucleophile. Okay, well, what charge was our nucleophile? Negative. And it didn't have to be negative. It could just be a neutral thing, but it is supplying electrons, which means what part of my protic solvent needs to interact with my nucleophile? The positive of our hydrogen. So what we're talking about is generating this interaction. We'll go ahead and call it blue because it's water. Why not? All right, and we get that interaction. Officially, we get a ton of those interactions, and we could go through and draw them all, but I don't have enough time, so I'm not going to do it. Okay? We could also go through and look at it for the other nucleophile, our bromide. And what this question is ultimately now asking is, are those interactions the same? No. And we would know they're not the same because what we would need to fall back to is our reactivity differences, again, going back to Unit 1 and dealing with intermolecular forces. The intermolecular force in that top case is now more or less hydrogen bonding, and in the bottom case, it's
Electrostatic. Sorry.
We've got to be a little bit careful with that because by you saying electrostatic, you're saying the bromide is being electrostatic, but the nitrogen was also equally electrostatic. Okay? So if we're going to call the top one hydrogen bonding, what do we need to call the bottom one? Maybe a dipole or a weak hydrogen bonding. Okay? We wouldn't even really call it hydrogen bonding because bromine is not nitrogen, oxygen, or fluorine. What does that mean for us? The hydrogen bonding interaction is a stronger interaction. That stronger interaction, for the nitrogen to now act as a nucleophile, we have to break a stronger interaction so that it can get out and react with the electrophile. So what does that mean? Nitrogen's stuck in the solvent. Bromide's free to move. And if the bromide's free to move, that's going to mean it's going to act as the stronger nucleophile. You mean it just switched? Yes. Your nucleophilic characteristic is heavily solvent dependent, and we have to be real careful to consider the solvent, right, when we go through and evaluate. Kind of, sort of? Okay. What happens if we switch to any other solvent? Okay. If we switch to a polar protic with our acetone, yeah, we're going to create an attraction within there, right? And we could go through and do it with the other one. We're going to create an attraction within there. Okay. Is that attraction ultimately that different? These are now going to be both relatively similar dipole or ion dipole forces, however you want to define that. Okay. And if their strength of attraction is similar, are we going to see the solvent affect the nucleophilic characteristic? Not really. Okay? And ultimately, you will see that the textbook pushes and says, well, it does have an effect, but ultimately the effect is coming down to really saying there's no effect. Okay? And really all they're saying is that bromide being larger has more solvent molecules around it. So for the bromide to act as a nucleophile, what do I have to do? I have to clear away more solvent molecules than I have to clear away for the nitrogen. Because I have to clear more crap out of the way, that slows the bromide reactivity, which means nitrogen's the stronger nucleophile. Okay? And so our polar aprotic or even our nonpolar are effectively not solvent examples. The only one that switches is our protic solvent. That's where we've got an extra little line that we've got to watch out for, and it's because the strength of the attraction between the solvent and our nucleophile changes. Kind of, sort of? Okay. I personally hate asking that question with the solvent dependence, and so typically do not ask it. The only reason why it was asked now is that was too easy of a comparison, and so I had to make it more difficult. If we look at the way the question is phrased, it's saying nothing about solvent, so don't make it more challenging. Okay? If you did, on the case of the exam, and say, well, in a protic solvent, be like, show off, but here's your full points. As long as you did it correct. Okay? But that becomes the problem, is you would have to do it correct by adding that extra layer of complexity. Make sense? I was hoping it also said ignore solvent effects. We good with that? There was a hand.
I mean, so in a protic solvent, it's the better nucleophile or the more.
Tend to be the bigger ones
Okay. But
because they get less hydrogen bonding interactions.
so I guess it's just the question is phrasing it as just look at the.
So yeah, the initial question just said, look at them. There is no secondary solvent effect that's mitigating any of this. Just tell me what it is. Does that make sense? Okay, I feel like erasing everything. Which then takes us to the last one. The last one, I would argue, is the trickiest of all of them. Any ideas why? These two species can act as
Both acids.
an acid, or a nucleophile, or an electrophile. Okay? So circling any one of those three is perfectly acceptable, okay, for this last one. I think the first one you could kind of get away with too. It's a little bit trickier, but you could pull that one off. Okay? So with this last one, we can pick any of those options. I did try to pigeonhole you into one answer. Right? The one answer that you would hopefully jump on is what's the reactivity? Acidity, because back in Unit 1, when I told you to memorize the functional groups, you memorized that that functional group is a carboxylic acid. There's your answer. Okay? If you didn't memorize that, you could have picked any of the other ones. I think it does make it a harder thing to go through and compare, but you can go through and do those. If we're looking at it acting as an acid, similar to what we talked through, but I don't think I did a good job boxing it in. Actually, I think I did. Okay? We want to identify the thing that's acting as an acid. What's the thing that's acting as an acid? That hydrogen at the end. Okay? To evaluate acid strength, just like we do with all the others, what we want to move through is looking at comparisons between charge, size, electronegativity, resonance, induction. In the previous two examples, we looked at nucleophiles, okay, or electrophiles. Okay? In both of those scenarios, it's relatively easy to just manipulate the electrons within the structure. Acids become a little bit trickier to deal with because how do you move the electrons? The only electrons we're really talking about are the electrons holding the hydrogen onto the structure. Can you do resonance with those? No, those are sigma electrons. Okay? So typically when we move to acid ranking, what we almost always do is instead of looking at the raw acid structure, we look at its conjugate base. And we look to the conjugate base because when we draw out the conjugate base, what do we see? We see a charge. That charge is now something that we can grab a hold of and we can start to manipulate as far as the structure's reactivity goes. Did I draw that one right? I did. Okay? So we could go through and start to make a comparison between these to identify that difference. We could start with charge. They're both oxygen, both negatively charged, no difference. Then we move to size. It's oxygen versus oxygen, no difference. We could move to electronegativity. Okay? Again, both oxygens. Doesn't work. We could move to resonance. Do they both have resonance?
Yes.
Yeah, they both have resonance. The exact same resonance. So again, no effect. Then we can move to induction. Induction is now going to explain our difference, because now we do have a difference. What we're comparing is this carbon to this nitrogen. Seeing the lone pair on the nitrogen can set people off and go, oh, I got resonance. Be careful. We don't have resonance because the carbon next door is sp3 hybridized, and we can't pass electrons through that, which means there is no resonance coming from the nitrogen. Okay? So the difference is carbon versus nitrogen, and what's our difference? More electrons isn't going to do anything because more electrons is really a resonance argument, okay? Or even a steric argument. Neither of those are explaining anything about what's going on with that negative oxygen. The biggest difference between those two that has any effect is electronegativity. Nitrogen is more electronegative than that carbon. So what does that mean? I'm getting electron density within the sigma bond being drawn towards that nitrogen. That means what I've identified as my blue carbon is starting to lose electrons. So what does it do? It reaches out to its neighbors to pull electrons towards it. And then that carbon's like, well, crap, I'm losing electrons. So what does it do? It reaches out to its neighbors to pull electrons towards it. And so what we're seeing is the electrons on that negative oxygen getting pulled into the structure. To run a chemical reaction, by definition, where must the electrons go? Outside the structure. So if I'm showing a system that explains the electrons getting pulled into the structure, what does that mean happens to its reactivity? It goes down. That structure becomes more stable. Okay? And now we've got to fall back to all of the stuff that theoretically we picked up from 152 and then swiftly forgot, right? And dealing with acid strength. The more stable your conjugate base, the stronger the acid, which then means this structure is a stronger acid, okay? Due to, yes, it's more stable. Why is it more stable? An inductive effect. Okay? So if we go back through and look at each of these examples, we're choosing which one's acting as a nucleophile or electrophile, okay, or acid, and we're choosing that and ranking their abilities based off of charge, size, electronegativity, resonance, and induction. And if you go back and evaluate them, they're all different. This one's looking at an inductive effect. The first one was looking at resonance. The middle one is looking at size. Okay? So if you were going to plan ahead for an exam, what might you try to consider? Let's pick some random structures and see if we can explain how their chemistry is different based off of electronegativity, based off of resonance, based off of charge. And if you can explain that, you're already a step ahead with whatever question I could potentially throw at you. Kind of, sort of? Questions? How did you feel about the exercise? Some people feel okay about it? Okay. We can try and leverage and push that a little bit more. We'll just see kind of where it takes us. Okay. But what you're trying to think about is ultimately the biggest thing is talk to each other. Okay. Force each other to explain what's going on. Sometimes you need a little bit of impetus from the outside of someone saying, I don't understand, to force you to make that explanation. Right? In my overview, I don't think anybody said I don't understand. Except one person. One person said that. Who said that? I said that virtually every time someone came up with an explanation. Okay? You need to be able to have that, but I don't understand, and then force somebody else to push that explanation deeper to get to that level of understanding. Okay? You all are amazing. Keep up the work.